Daddy, can you try to share your screen, please?
So yeah, we have 6 speakers.
Yeah, this is Tom Sako. Do you hear me?
Hi, Tom.
Hello.
How are you?
Hi.
Yeah, I'm good.
Can you try, Tom, to share your screen?
Yes.
Hi, Peter.
This is my screen.
Yeah, we can see your
perfect, Tom.
screen.
Okay, good. Thank you.
Yeah, thank you.
Daddy, I will leave you manage the room.
All right, thank you. Thank you, David.
I will stay behind if you need me.
Yeah. Bye. Hi, Alex.
Hi, how are you?
Yeah, good. Yeah, should we ask every speaker to try sharing the screen first before we begin the session?
Sure. Is everyone here?
I guess so. We have 5 speakers, but we have one more speaker from yesterday. So in total, we should have 6 speakers for today, 6 presenters.
I can see Mariam. I don't see Saber though. Meth, Kirsty.
So yeah, okay. For those of you who have tried sharing the screen, maybe you can turn your microphone and video off, and then we will call you when your turn comes. So could you, Oliver or Peter, share your screen?
Yes, I can try. Is the best to share the entire screen or to try to share the application?
I guess the entire screen would be good if you have something other from your presentation that you want to show to us. Yeah, so we can see it.
Fine.
Yeah.
Okay, so now I try to share the screen. Is it working?
Yeah, we can see your screen.
Also the presentation mode?
Yeah.
Yep.
And so we have one more presenter, Saber Kayatzadeh. Yeah, Mariam, we can see your screen. Thank you.
Yeah, thank you.
So we have one more presenter. Alex, could you give some house rule information to all our presenters before we get started, since you are the chair of this session?
Okay, I'll ask them to mute themselves, I guess, and share their screen where they're up for a presentation.
Could you try sharing your screen?
Moving my laptop to the right position, so I got your voice. I'm just going to give you a camera in a minute.
All right, no problem.
Hi there. Yes.
We can see you.
Great. Thank you.
Do you want to try sharing your screen? Yeah, your screen.
Yeah.
So we can see your presentation.
Sure. Yeah. Here we go.
Perfect.
So you got the presentation then? Okay.
Yeah.
Brilliant.
Okay.
Shall I stop sharing?
Yeah.
Thank you.
Yeah, thank you. So I think our first presenter is Tomohiko, right?
Okay, I think I'm the last one for this session, right?
Yeah. All right.
Brilliant.
So, Tomohiko, if you can start sharing your screen now.
Yep.
Yep.
So I think we will begin in 3 minutes.
Yep.
So Alex, do you want to introduce yourself first?
Hello, everyone. Welcome to this session. It's nice to be with you even virtually. Some instructions for, let's all keep it muted while we're not speaking, and maybe also save bandwidth by keeping the cameras closed. When your time is to speak, you can open up to your cameras so that we are able to see you if you want, of course. And then during the presentation, we can switch it off again to save bandwidth. And now, in terms of questions, I'm not sure how many the participants will be. Maybe it's a small session, maybe it's a large one in terms of audience. So if it's a small number, maybe we can directly ask when I say the presenter, perhaps by raising hand, or you can fill in your question in the Q&A in the chat box on your right. So we will be starting in 1 minute or something. Teddy, am I forgetting something?
Thank you, Alex. So my name is Dedi Aryansha. I'm a research fellow from Cranfield University, and I'm the co-chair of this session. So yeah, I hope that this session could be useful for us. I hope that there will be an interesting discussion for this session. And yeah, please remember that every presenter has 15 minutes presentation and 5-minute question and answer. So for the attendees, you can post your question in Q&A if you have any questions. And yeah, we will try to present your questions to the presenters. I guess that's it from me.
Just a small thing, it's the wrong name. It says Jay Lindström for me, but it's my name is obviously Petter Kjösti. So John couldn't make it. It was in the agenda in the auditorium.
Okay. Yeah. So so you'll be the presenter for the paper, right?
Yes.
Okay. No problem.
Okay,
I think we
the
can
third
get
one, I guess.
started, Alex.
Okay. The first presenter is Tomohiko Sakao, and the presentation is a product service system design schema application to big data analytics. Please, sir, feel free to.
Thank you. Thank you, Chairperson. Do you hear me well?
Yes, loud and clear.
Okay, good. Thank you. In this presentation, I'm going to share with you our research results that have been already published on the journal Sustainability, published several months ago. The publication is entitled in the same way as in this presentation. It's about PSS design schema, which I will explain later, and also its application to big data analytics. So basically, this research has three contributions. Number one, we provide a unique schema for PSS conceptual design because currently there are a variety of different research results, useful insights in literature for PSS design, but it's quite hard, especially for practitioners, to get hold of what is there and what can be useful, etc. To do this, we used literature, and we use systematic literature review, but we focused on literature synthesis. It's a part of systematic literature review. Secondly, because big data analytics, as you know, has gained attention for the last years, PSS has been there for a while. So we are interested in what could be relations between those two body of knowledges. So we provide here one nexus between PSS design and big data analytics. To do this, we also used literature, but we also used literature synthesis based on these two disciplines. Number three, it's a theoretical contribution. We provide an account for intra and inter literature synthesis, meaning that literature synthesis within one area and literature synthesis between two different areas. Because as you know, there is a sort of insanely growing number of systematic literature review articles. Their impacts are quite unknown. So to cope with this kind of problematic situation, we provide one way to cope with this in order to provide really practically useful knowledge for, especially for practitioners. We have three research questions. The first one is already, as I mentioned in the previous slide. And number two, we focused on what have been done and also what are the opportunities for further research. And number three, we have also interest in implications on environmental sustainability by applying big data analytics in PSS design. So as I mentioned, literature review, focusing on literature synthesis was the method used. And on the left-hand side of this slide, as an outcome of literature synthesis in PSS design area, we get a consolidated schema for PSS conceptual design. A schema is a concept quite common in psychology or cognitive science. It's in this context, it's a structured outline of procedural aspects that could be useful during PSS conceptual designing. Because basically, a professional in a certain area has his or her own schema, sort of framework, by which he or she can use newly incoming information effectively and efficiently. Meaning that if you ask a PSS design professional, they have already some sort of established knowledge and framework in themselves, so that new insights coming in, for example, from big data analytics, they can use new knowledge coming from another area effectively and efficiently. So that's the idea. So in a way, the design schema is prescriptive, but we hope this will be useful to explain how big data analytics could be used in PSS design. And as you can see at the bottom of this slide, we combine the results of literature synthesis in PSS design and also in big data analytics. So this corresponds to interdiscipline literature synthesis. So looking at the results from PSS design literature synthesis, so we addressed 10 rather well-known review articles, and we extracted 5 common facets from those review articles in PSS design. So in a way, we did a meta-analysis of by using the existing review articles. So as you can see, functionality-oriented designing, including relevant actors in the ecosystem, value propositions, integration of system elements, and the examination of the balance between the product and service components. These are the 5 facets that we identified. So we used those 5 facets that you look at in the middle of this slide in order to make a PSS design schema. To do that, we also used very well-known engineering design methodology developed by Paul and Bites. So it was developed in the area of engineering design, but it is deemed feasible to use this as a sort of mold where we pour the 5 facets from PSS design into it, and then we get PSS design schema. So Paul and Bites design methodology is commonly described as these 7 steps, to simply put, and then we apply these 5 facets to obtain these 10 steps for the proposed PSS design schema. So in a way, we built upon Paul and Bites design methodologies, and we applied the sort of characteristics or peculiarities from PSS design, and then we obtain a sort of design framework, design methodology that we think useful for PSS design. Looking at the BDA area, we use the keywords for the literature such as big data analytics, product or service or product service system, and design or development. So we aimed to capture different publications that are relevant to big data analytics and design context. We found 117 articles from the keyword search, out of which we identified 11 articles that handle real industrial cases. So it's interesting to see a rather low number, low ratio, meaning that 11 out of 117 addressed industrial cases. And 2 out of the 11 are on this slide. The first example is a little bit related to the example that Professor Andy Neely mentioned earlier this morning. it's about infrastructure in society. So in this case, they analyzed the conditions and design characteristics of different bridges in USA, so that the useful information, for example, for maintenance and of course inspection as well, are obtained. And they used ANOVA as a method for PDA.
Excuse me, this is a 5 minutes notice.
Yep.
Yeah.
And we, when we sort of applied the knowledge that we can capture from big data analytics cases into PSS design, we used this kind of frame. This frame shows product design and service design in terms of how information is transformed. Okay. And we further looked into what are the data sources that could be used for big data analytics, and what are the targets of applying the information coming from the data could be used in design. As you know, production of physical products is always associated with some kind of deviation because of the real world constraint. So there is one place for the data sources, because there are huge amount of data could be created. And also in the use phase of the products, it's always products deteriorate in their quality. So that's also a sort of place where the big data can be created. That's the same with the service production and use. Now we can see these are the data sources, and also the targets of the information from the data could be used in product design and service design. So these green arrows indicate the application of the data and the information within the product or service boundary. But on the other hand, you could, of course, use the product-related information in service design and vice versa as well. It's a cross-boundary application of the data into design. So this slide is a sort of integrated part of the result. On the left-hand side, you see the PSS design schema that we propose. And in the two columns, you see the data source and the targets in design. So the letter T indicates the combination of application of big data into the respective steps in the PSS design schema, at least theoretically speaking. And mapping the literature review results from big data analytics onto this table, as you see, some articles cover what we think theoretically relevant, but there are open spaces that indicate research opportunities. Thank you very much. I hope this is interesting for you. Any question? Thank you.
Very clear presentation and very interesting topic. Let's begin with the audience. Are there any questions?
So maybe to kick off, I have a question. So how do you validate the schema that you develop for PSS?
Yeah, validation is not necessary within this research scope, but we can argue within this research scope, we can argue that this is very much built upon the widely used design methodology that is from Paul and Bytes, and we sort of added some characteristics of PSS design. But just for the information, we are using this design schema in order to show the improvement in the design we are conducting design experiments where we apply this design schema for one group of designers, and we also conducting experiments without this design schema for different designers as a control. So we are comparing the design sort of quality from those two groups. By that, we want to show the quantitative sort of difference or impacts of using this design schema. That's, I mean, yeah, we are doing that research outside this research.
Yeah, thank you, Tom. So is there any questions from attendees or other presenters? So we've got one. So from Mariam. So as you know, life cycle cost estimation is the key when designing PSS. Where does it fit in your proposed framework?
Life cycle costing, that is related to number 5, criterion identification, and step number 9, evaluating combinations. Especially step number 5 should involve different indicators to be evaluated later on within the design, and at steps 9, when suitable and when resource is available, life cycle costing could be performed.
Okay, thanks.
If I may ask also, how did you identify the out of the 117 papers, the ones that had the industrial added value?
The choice of the 11 out of 117 is rather easy. If you read each paper, then it's clear if the paper addresses real industrial case or not. And basically, roughly 90% of the publications don't address real industrial case.
So you eliminated the ones that did not have a case study or were purely simulations and things like that.
In this specific research, right?
Yeah. And in your opinion, just to have a follow-up question, what are the challenges regarding to business and technical aspects of the PSS under the scope of big data, of course?
Okay. Actually, yesterday we presented another abstract. So we see several challenges. Practically speaking, one is organizational challenge. It was touched upon earlier this morning by the gentleman keynote speaker from Babcock. He mentioned that the sort of company-wide view is sometimes necessary to make a plan for developing and deploying a certain system, because a number of different actors, different sectors in organization will be and must be involved when it comes to product service system, because that relates product services, etc. So that is for sure one big challenge, practically speaking. And we mentioned also another challenge area, which is how to manage different types of uncertainty. So that's also a big challenge.
Okay, very clear. Thank you very much. Thank you also for your work and your presentation. And Daddy, can we move on to the next?
Thank you.
We can move to the other presenter. Thank you, Tom.
I see in the program the presenter is Katja Guce. I'm not sure if that is the case.
Katja Guce, yeah. I don't see his name in the list of participants.
Is there a substitute, if I may ask the speakers?
So from what I see from the document, he's the only author of the paper. So maybe we can, because
can you check the tables?
Yeah. In the meantime, maybe we can proceed to the next participant. I will ask if if he's around.
Okay. Let's wait 1 minute.
Go on with the third one. I will check for Katya. Okay.
Okay, thank you, Davide.
No worries.
I'm here.
So Peter
yeah.
Kirsty?
Yes, exactly. So I will replace Jon Lindström, who is the main author of the paper, but we have written this together. The rest of the authors are industrial, so it will be fine.
Okay. Feel free to proceed with the presentation whenever you're ready.
Sure. So this paper is called Zero Defect Manufacturing in an Industry 4.0 Context, a case study of requirements for change and desired effects. I come from a cluster organization at Luleå University of Technology in northern Sweden. So we work with the companies and industry, basic industry, process industry, manufacturing industry, to produce projects mainly. But I have a background to working with the functional products and PSS and servitization before, so this is sort of a evolution of that work, I would say. And also with me, Jon Lindström has also that background. So all of the rest are, as I said, from industry. The agenda, first, it's based on the paper. First, an introduction, background, related work, research approach, findings, analysis, discussion, and conclusion. The problem that we have identified is that since technology has rapidly developed, there's need for an updated and comprehensive general set of requirements regarding zero defect manufacturing, because that's an old concept from the 80s, I believe, as part of total quality management, but it was deemed out to be with too high aims and insufficient technology to be able to achieve it. So what we have looked at is it's a case study for 6 different companies. We look at the requirements for change, problems, needs, and desired effects. Yes, as I said, it's part of a total quality management, but it was also too much management perspective, too much consultants involved. So we're taking a new look at this with all the new technology with that we have in the industrial Internet of Things, and we have Industry 4.0, and we also have this growing capability of machine learning and how that will play out. So this is the current CDM from Soramatis in the early 2019, and it's based on both a product and the process perspective, so that you gather data and then you make a data analysis together with these two to say something about what the state of the product is and what the state of the machinery is, which should give some advice to what to do. And what we have done is then looked at the information flow and how this can be improved and what is required. So we have some sort of manufacturing process in the center, which is common for all of our stakeholders. And what we need is some kind of a measurement at the end, inline measurement, and we already have a lot of process parameters from different systems, which could say something. And we also have data from input material that could be used. But this is a sort of a wide problem, and there are already systems for all the subsystems to check the quality. But what we want to do is to merge these through interoperability, and Arrowhead Tools is the system that we use. So it's a collaboration between different research subjects at the university. It's control engineering, it's data integration, and it's vision systems that's collaborating in this. And the aim is to give advice, we could call it, both to humans and directly to machines, how the process should be adjusted to achieve zero defects. There are, of course, quite a lot of related works concerning this in the improved knowledge finding, knowledge feedback, signal processing, critical parameters, quality control, and monitoring systems, and also quite a lot of desired effects and the cost reduction, higher efficiency, and less scrapping. So we decided to have an extra look at this, and the case review, a case study based on YIN. And these are the companies: Gestamp Hartech, they make auto parts, crash details; Volvo Cars, Scania, who makes trucks; Väling makes floors, wooden floors; an unknown company, and also Swedish Steel. So this process should be common for all these companies. Research question is, why do the manufacturing and process companies want to address CDM in their production process? So we want to look at the requirements for change. What we did was semi-structured interviews and workshops, and analyzed it through matrices. So the findings is a couple of tables. First, of the perceived problems, unplanned stops and quality outside specifications. What's the first one? Yes, sorry, we categorize this also according to the rightmost column. C is E is efficiency, V is value chain, Q is quality, S is skills and competence, R is resource, and G is gender equality, and P is profit. So unplanned stops is the first problems, and the quality outside specifications, defective products or parts, which reached next step in the value chain. And this is one of the biggest problems, I would say, since they have no way of communicating between each other in some instances, and in some ways it's different companies. So if you get something from a supplier, it's really hard sometimes to communicate. Or if you ship it to a customer, they have certain demands, so it can be quite tough to make improvements. And also, we want to avoid producing out of specification products and parts, of course, but we need to be able to detect it. And sometimes you only make batch, one part per batch is controlled, or at certain intervals, which gives sometimes too little information. It can be very difficult and expensive and time-consuming to test these investments. It sometimes requires advanced monitoring systems, or the output from the existing monitoring systems are quite limited. Also that large quantity of the data that are produced is not used, or is in a format that is really hard to use. And also what we see is an increased complexity of the products, so there's less margin for errors. Next is the needs perceived by the 6 companies. Traceability through the value chain is something many of these have voiced that is needed, but it can be tough also if they don't have a good marking method or a data collection method. They want to be able to detect and predict problems, and to be for this problem to be sort of contained in the digital twin or in the data context. So to be able to do this, they need monitoring and knowledge about the logistics and the production processes, so that they can avoid unplanned stops, of course. So they want to have a high level of availability, which can be trusted. And that's also a main goal, to have the process to be more predictive when quality of the machinery is starting to decline. And some of this is done already, but some is not. And also, if we can keep an assured and even and specified level of quality to be sent to next step, we can also improve, either to increase the quality or to take that into account in the next step of the production chain. So the desired effects that we have discovered is less material used.
Excuse me, Peter, there are 5 minutes to go.
Yeah, sure. Thank you. And less material and energy used. If you don't produce scrap, then you produce something that you can sell, which makes it that you don't have to use as much energy and material. There's also sometimes trimming steps, which can be reduced if you all can maintain higher quality in earlier steps. And also, if you have higher trust in your own production process, then you can avoid bottlenecks, and you can actually produce more in the same calendar time. We have also seen that increased generic quality is a driving force in this, since it's a very male-dominated industry, all of this. And with the increased analytics and new technology, we have a bigger base that we can recruit from. So we have a lot of unused data. We have this decreased margin for errors, so we want to decrease. This is a way to reduce the resource consumption and to increase efficiency and profitability in a way that's actually one of the few ways forward that can make actual impacts. But the most important part is the last point here, that with this holistic view, that we take data from different parts or sub-processes, then we can discover new problems or inefficiencies that are otherwise hidden if you only look at one of the sub-processes at a time. But this will also require to have collaborations both horizontally and vertically, so both with the suppliers and customers and machine vendors. So, and for each production step, you need to really dig into the problem and try to get this all into one common digital twin is the way forward as we see it. And to be able to make a model which you can improve in iterations, then you can also improve the data quality that you get from this. And since this paper is from 1 year ago, which is then data from 2 years ago, of course, we have continued working on this. So right now we have a ready consortium of these companies, and we have sent in an application to which we should get the answer to soon if we can start working with this and implement these changes actually. So we have contributed to literature with the aggregated view from the 6 process manufacturing companies to practice with desired effects which they want to achieve the industry. and to managerial contribution is input to strategy discussions on how to invest in higher quality. The results are highly generalizable since it's so many industries involved. When what we see is that CDM 4.0 can improve competitiveness, profitability, and attractiveness for workers and engineers. And it will enable them to grow and better handle variations in business climate and business cycles. Thank you.
Thank you, Peter. Very dangerous topic, I dare to say, zero defect manufacturing, but you managed to keep it in a formal approach, a systematic approach that can be used. If I got it right, you mainly raise integration issues, right?
Yes, data integration is the main issue.
So if I may ask, what in your opinion would be the catalyst for zero defect manufacturing techniques? What techniques are more efficient in terms of data processing, for example, to achieve zero defect manufacturing?
Well, there is a lot of European initiatives right now for data integration. And about this evolution of these standards right now, like we are involved in the Arrowhead project, which I think is central, but it's also PyWire, Apache, the Linux Foundation, I think. So what we don't want to do is develop new standards or have it proprietary, so that, for example, Siemens develop their own standards and lock their companies in. We want to have it sort of in a EU level, is I think the way forward.
Thank you.
So I have sorry, Alex.
Yeah, I can go ahead.
You want to continue? Yeah. So I just have one question. Can you elaborate more in terms of when new materials or new technology are introduced in manufacturing industry, what are the steps to or the approach to monitor and control in order to ensure zero defect manufacturing? Like, how do you control the uncertainty introduced by new materials or new technology?
Yes, this is, I think, related to first adhere to the standards of data integration, but also then have a model or a digital twin of the factory so that you can manage uncertainties, because there will be uncertainties and things will change daily or monthly or yearly, so that there are many directions that you need to work in at the same time. But to have a model that allows for uncertainties is a good way, and to build on that, because it will be a lot to begin with, and then to have this parameter be reduced by increased information and knowledge.
Okay, thank you, Peter. So are there any questions from participants? Nope. So thank you, Peter. Thank you for your presentation. And should we move to the next presenter, Alex?
Yeah, we could do that. Who is online? Is it Oliver? No?
Yeah, Oliver.
Okay. Oliver Merth.
Yeah, hello, I'm here.
Hello, welcome. Can you share your screen?
Yes, just trying to turn off my camera. Turn on, sorry. No. Okay. Hello?
Yes, we can see
hear
you. So the title is Design for Life Cycle Uncertainties, Design Principles that Enhance Coping with Uncertainties through a Product Life Cycle.
Yes.
Whenever you are ready, Oliver.
So you can see my screen?
Yeah, it's full
Perfect.
screen now.
So thank you for the introduction. Yes, my name is Oliver Matteo. I'm research associate at the Institute of Innovation and Industrial Management at Graz University of Technology, and today I'm going to present you a paper designed for life cycle flexibility, design objectives that enhance coping with uncertainties toward a product life cycle. I've divided my presentation into 5 parts. First, in the introduction, I'm going to present you the problem statement, the aim, and the research question of this paper. In the second part, going to show you relevant design guidelines that were investigated and the resulting design catalog that contains design objectives and design principles. And in the fourth part, I'm going to present an approach for the selection of appropriate design objectives in order to enhance coping with lifecycle uncertainties. And finally, I'm going to conclude my presentation. The product lifecycle is characterized by a high degree of uncertainty. Sudden changes of customer requirements during the development phase, demand fluctuations or supply disruptions during the production phase, unknown future user needs or unknown future operating conditions during the operation phase, and stricter legislation during the end-of-life phase are some examples. Researchers have been investigating several concepts to cope with such as lifecycle uncertainties and also the resulting changes. And as common enabler, only an appropriate product design enhances coping with them effectively, efficiently, and proactively. The high importance of product design to cope with such uncertainties is further underlined by its strong influence on the committed cost, change cost, and potential cost throughout the entire life cycle of a product, as shown on the right here on the right side of this slide. Based on existing strategies in the literature for coping with uncertainties and changes, 2 own principles have been derived. On the one hand, the prevention of changes, and on the other hand, quick and low-cost reaction to changes. In order to achieve significant benefits with the reaction principle, specific company requirements, for example, late product differentiation, but and specific product requirements, for example, simplified assembly or simplified disassembly are essential. An appropriate product design enhances fulfilling these flexibility requirements now proactively, effectively, and efficiently in order to cope with lifecycle changes. Therefore, the aim of this paper is to understand how product design can enhance coping with lifecycle uncertainties and changes. And this results in the following research question: how can product design and flexibility requirements be systematically linked? Research efforts in optimizing product design have led to over 75 different DFX guidelines. In order to link product design now with flexibility requirements, design principles of 27 DFX guidelines shown in the right table were collected. These guidelines were seen to support one of the 2, or at least one of the 2 principles mentioned earlier, to cope with changes. Furthermore, it was also important to cover the entire life cycle. The identification of relevant publications was based on 2 pillars. First, 2 review papers about DFX guidelines provided 264 relevant publications, and additionally, a systematic literature identification was performed using the database Scopus and also specific keywords that you can find in the paper. Yeah, and so 7,168 potential publications were identified. That's of course quite a lot. So the next step was narrowing them down at the beginning to see which paper even mentions product design principles or any synonyms of it. And so the remaining ones were then compared with them from the review articles, and this has led to a final number of 92 investigated publications. Good. So in total, more than 1,700 design principles were collected, and summarizing similar ones and eliminating duplicates has led to a final list of 650 different design principles. As many of these principles have also similar purposes, they were further clustered into 24 design objectives and 16 support objectives. So the design objectives aim to facilitate the procedure of selecting appropriate design principles to enhance fulfilling the defined flexibility requirements, and the support objectives, on the other hand, just aim to enhance the related design objectives. Good, so design principles are allocated to objectives according to the first, and if available, also second purpose. The left table on this slide shows exemplary design principles of the design objective product modularization. So while modularization is the first purpose or the only purpose of the first three design principles, you can see that the other 5 principles have, besides product modularization, also a second purpose. For example, product differentiability or recyclability, and so on. Yes. Besides that, also detailed information, which paper mentions which principles regarding which DFX guideline was collected. And so it was possible to calculate this a DFX share. So this represents the ratio of the quantity of guidelines mentioning the principles over the total quantity of investigated guidelines. So the DFX share allows statements about the importance of design principles to enhance coping with lifecycle uncertainties, and as shown on the right table, highly important are using modular design, using standardized component and part commonality, and also to reduce the number of components and subassemblies. Good. In the next step, the relevant product and company requirements to realize an appropriate flexibility must be defined. So a possible approach for that is based on the double diamond design process from the British Design Council. And you can see the first diamond on the left side starts with the identification of potential uncertainties and changes that might affect a product through its entire life cycle, and it ends with the definition of critical or relevant changes based through a qualitative assessment. The second diamond then starts with the identification of potential flexibility requirements for coping with the previously identified critical changes, and ends with the definition of the relevant requirements to another quantitative assessment. Okay, so once the product design objectives and the flexibility requirements are identified, or the relevant flexibility requirements identified, it's possible to link them to the employment of a domain mapping matrix and design structure matrix. So therefore, the first step includes the weighting of the importance of the product and company requirements regarding must-have 9, should-have 6, nice-to-have 3, and no need 0. And the second step is the assessment whether a specific design objective positively influence a requirement, then putting a 1, or not, then putting a 0. So this is then performed, and then the design mapping matrix, DMM, here also marked in blue, is completed via multiplying the values of these dependencies by the values of the importance of the requirements. The DSM, the design structure matrix, is then calculated to the multiplication of the original matrix with its transposed version, as seen on the right side of this table, of this slide. And the table also shows sample results, whereas the periodization values of the design objectives are shown in the main diagonal in orange, and dividing these periodization values by the maximum, in this example here 243, results in the periodization percentages displayed on the right side, and these percentages indicate the recommended priority of applying design objective and the related design principles in order to realize the corresponding product or company requirements. Here I also want to mention that all these numbers are just samples, so it's not based on any data collection or not on any industrial case. Okay, thank you. Okay, so let's come to the conclusion. And the only an appropriate product design enhances coping with uncertainties in life and changes toward the product life cycle effectively, efficiently, and proactively. Based on a systematic literature review, this paper introduces a design catalog that contains 24 design objectives and 16 support objectives, whereas each of these objectives includes further design principles. A possible approach to define requirements to realize an appropriate lifecycle flexibility based on the double diamond design process is also introduced, and the product design objectives can be linked to with the relevant flexibility requirements to the employment of a design mapping matrix. However, the evaluation of the final 650 design principles and also the design objectives is still to be performed. Also, the evaluation of the selection procedure model is still to be done, and further work is also required for the approach to define relevant flexibility requirements, especially in identifying appropriate assessment criteria. So I told you before, there's the end of the first and the second diamond, there are two quantitative assessments, and this criteria for this assessment is also still necessary. Finally, the mutual dependencies among the design and support objectives should be also considered for the actual selection process. So this was my presentation. Thank you very much for your attention. Now I'm open for any questions.
Thank you, Oliver. Very interesting indeed. If I may ask, what is the impact? What are the repercussions for the company with respect to this evaluation of the priorities?
You're talking about this slide here with the numbers, or?
Yeah. Yes.
So, so this slide, these numbers here more or less have no meaning. It's just to show that we did it once with a company, that's true, but only with one participant. So they are not general valid. And I also have to say that it's not possible to give here general valid or numbers or privatization values, simply because each product is different, each project is different, each development project is different, each company is different. So, however, what it means is we can see that simplification, the highest number has, can I do this? Here, the highest number has standardization. So it simply means that standardization has the highest positive impact in realizing the previously defined product and company requirements.
Okay.
The lowest impact has integration. I hope this answered your question.
Yeah. Thank you. And there are also two questions from the audience. The first one is from Mariam. Design the service for products is crucial over the product life cycle. How does the outcome of your research consider this?
Sorry, I didn't understand the question.
Design the service for products is crucial over the product life cycle. How does the outcome of your research consider this?
Yeah, you can see on this slide here, these are all the design guidelines here on the right side I have investigated. And you can also see that I considered design for serviceability, design for maintenance, design for support, also repair. So I collected many design principles also from these guidelines, and they were of course also included. So, however, what I did here is I removed the principles from such guidelines and tried to combine those principles with similar purposes. For example, design for serviceability. One important principle is that some components are you can disassemble them and replace them, but also other guidelines, for example, design for modularization has this principle. So this is how it's included or considered.
So if I got it right, the idea behind this table is that you can consider every design for X aspect.
Exactly. So I have really, through the entire life cycle, I've identified important guidelines. So also regarding or related to service, and these principles are then included in the final list.
Okay. If Mariam has a follow-up question, maybe she can proceed with it. And one more question from Tomohiko. In the principles and designs you are aware, did you find conflicts of the independence principle with any other principle of designs?
Of course, definitely there are conflicts. That's the reason why later there's this, or the final result or the output of this prototype model is a privatization percentage. It simply says start first with, in this case, standardization because it has the highest value, and then go to the next one. And so if there are conflicts, just focus on principles related to standardization first.
Okay, thank you. Actually, Tomohiko has a follow-up question. He's clarifying that he was asking specifically about the independence axiom from Su's axiomatic theory. I'm not sure. Okay.
Is that possible?
Yeah, go ahead, Mexico.
Oliver,
Just quickly.
nice talk. My question concerns particularly the independence principle. That is one of the principles that you presented in a slide. And my question is, do you know any conflicts between the independence principle versus any other possible principle in design? Because but the background of my question is many sort of academics and some practitioners believe in the independence principle, but it's believed in that is good to do. So in some cases, there are specific designs that don't follow that principle. So my question is, do you know different cases where you find conflicts between the independence principle and any other possible design principle?
With independence principle, you mean that, for example, each component has one or is connected with one specific function. So,
exactly. Yeah.
Of course, so there are examples in literature that show some where this independence principle makes sense, in other ones not. I don't have a specific example now in mind, to be honest.
Okay, thank you. Because the background of my question is because when we consider services in the design object, then I think it is more likely that dependence makes more sense rather than independence. So that's my background.
Okay.
But okay, thank you for your answer.
Thank you very much for your input.
Thank you, Oliver. Thank you, Tom. Alex, maybe we can move to the next presenter.
Yeah, sure. So it's
Thank you very
Saber Hayadzadeh, and the title is Through Life Engineering Services for Offshore Wind Energy. I guess we're moving to a different subject right now. So,
Hi there, yes.
Saber, when you're ready, please go ahead.
Yes, so thanks everyone for your time today, much appreciated. So today I'm going to have a chat about through life engineering services for offshore wind energy. This is a framework that we are working on collaboratively with other centers, especially Offshore Renewable Energy Catapult Center in Glasgow. And we try to implement the fundamental for tests into offshore energy and try to make it more profitable. And this part of work has been published with Dr. Himanshu and Professor Michael Ward, who's the current chair of Test Council in the UK. So obviously the content is, we're going to go very briefly through the through life engineering services and mentioning to pass to AT, just reviewing the market in offshore for offshore wind energy in the UK and briefly discussing the key drivers and the design for test. So during the today and yesterday, you received great talks from other candidates, especially from Professor Sam Turner and Professor Michael Ward, the ex and existing chair of Test Council for High Value Manufacturing in the UK. And they provided you with a great details on through life engineering services. Obviously, it's a business model, techniques, networking behavior and tools to improve the, reliable and predictable improvement for value in use of the assets and also expanding the life. Rolls-Royce or aerospace industry has been the key industry in terms of like pioneering tests, especially in the UK, and now we try to understand how we can take the lesson learned from this years of experience for implementing tests in aerospace for offshore wind, because offshore wind is less advanced compared to aerospace industry. during the past decade, there's been huge growth for offshore wind, but still we want to make sure that we are, we are effective in terms of generating electricity, especially offshore wind is highly subsidized by UK government, which is the taxpayer money. So PAS 280, which is publicly available specification published in 2018 by Innovate UK and a British Standard Institution. That was a collaborative work between key industries in the UK, like Rolls-Royce, Babcock, Doosan Babcock, and some other industry, ATI, and High Value Manufacturing Centers, and Cranfield University. So the framework of PAS 280 is regarding the organizational capabilities, value stream, and execution processes. So within this tree, we try to link all those parameters for the subcategories for each stage, basically. And what we are aiming to do here is we want to provide a common or generic framework which is applicable for SMEs as well. Because big companies like Rolls-Royce, they got their own team, they know, they got the resources, and they have the expertise to implement the test and following the rules and framework. But small companies, especially SMEs in the UK, they don't have that much resources, and we want to provide the backup to them, because they are the third parties that provide the services to the asset owners. And in terms of offshore wind energy, so where we are and where we're going in the whole UK. So basically, all started with the commitment that UK made in 1990s for reducing the emission by increasing basically the gross development value for the whole UK. That happens so far by 40% reduction to the CO2 emission, and the UK planning to reach 80% reduction by 2050 compared to the 1990. And offshore, renewable energy is been the main source of green energy, but the offshore wind has been one of the greatest one, and the first wind farm was set up in the UK in 2000. So there is a huge growth for that. Initially, onshore wind was overtaking the ground basically compared to offshore, but during the past couple of years, there's been huge growth for offshore, and simply because you got the opportunity to harvest more energy from the wind, and you can increase the size of the structure. And just to give you some idea of how much it works in terms of each wind turbine. So when you fly from abroad to the UK, when you pass the sea, so you will see lots of offshore wind assets. So roughly, on average, most of them are around 7 megawatts. So which worth around 20 million pounds each. So they are highly expensive assets, and it's very important to keep them safe. And in terms of the test framework, there are 5 key drivers as a generic key drivers. We try to follow them from offshore wind perspective, and obviously because test hasn't been defined for offshore wind, so there's a huge potential to implement it and reduce the subsidy that we receive from the government. UK is holding the biggest market for offshore wind in the whole world by 36% of the global market. So we need to ensure that we hold that market, but also increasing it. Initially, the government planning by reaching 2030 by 90 billion pounds. So the current market is around 30 billion pounds. But if you follow the news during the past few months, there's been lots of news coming up from the government that's backing up the plan. So this value would even increase by this, and they expecting to reach to provide green energy for the whole UK homes by 2030. And so far in Scotland, the Scottish government providing all the homes with the green energy, which is great achievement since last year. And obviously the test will provide a bigger market for the companies and who are active in the field. And obviously we're talking about the data and availability and enabling technologies. So in terms of if you want to understand how we can implement test framework to the new sector offshore wind here, we need to understand the gaps. We need to understand what's going on in the market. So therefore, we provided a full map based on the whole product life cycle, which is design, manufacture, commission, operation, and decommissioning. And we try to provide some examples per each stage. So obviously these are not the only one, but this is just the example. Something around 55 to 60% of the total cost of offshore wind has been spent for the first 3 stages of product life cycle: design, manufacture, and commission, which is a great number, and we need to reduce that. And also the operation would take something around 40 to 50%, 40 to 45% of the capital, basically, and the cost, the running cost, and the electricity is being generated by the turbines, which we need to work on that to see how we can implement or digital transformation that been talking since yesterday quite a lot. These are the buzzwords, and digital twins and advanced manufacturing, etc., to reduce all those costs. In terms of the commission, we don't have that much results. Obviously, there are some numbers around going on, but in the UK, we don't have that much. All has been a speculation, basically, in terms of numbers, but we don't have a solid numbers yet because we haven't reached the final life. The first offshore wind was 2000, and the life for offshore winds are something around 20 to 25, and the designers and the companies pushing it to 30. If we can extend the life of the current assets in the UK, but each year the UK government can save something around £2 billion for the whole assets, which is a great number. So what I'm going to do here, I'm just going to review all the gaps per each stage and try to mention them very briefly because I'm very cautious about the time. Obviously, the first stage is design. There are lack of standards, procedures, codes at the moment. Because offshore wind was taking advantage of the standards for oil and gas industry. That's how they started it, and that's been different structures. So it's very difficult to implement that for the floatable structure or some fixed structure, because the dynamic loading is different, and the service operation is different. So there is a huge demand. So companies like DNV working so hard to produce, a very valuable standards on that. Obviously, we need to increase the size because we want the bigger tower that we have, the more electricity that we can produce. Obviously, we don't have the experience before for manufacturing such a structure, so there is quite a lot challenges going on R&D, and we want to understand how we can verify and validate it as well. So lack of data, really. So how you want to validate something which you don't have data for this. And as you can see, the size of wind turbines keep increasing, and which is very challenging to install them on offshore. Another thing is, especially for Scotland, because the seabed is different from the England side. So we cannot use much fixed structure, so we have to have floatable structure. So this year, if you follow the news, this year we just had launched the first floatable structure in Scotland, which is great. This is another big achievement for the UK. So in terms of manufacturing,
excuse me, maybe you have 5 minutes to go.
So we, in terms of manufacturing, this is a very expensive process. We try to understand how we can take advantage of different techniques. So the cost is something around 22.5 to 3 million pounds per megawatt, which is a huge cost. And since UK holding 36% of the whole market, and we don't manufacture much of the structure, this is a key factor here that we need to work on. That's from the manufacturing stage. In terms of commission, this is one of the biggest stages. As I said, we don't manufacture much in the UK yet, so we need to import all the parts, everything from other countries like Spain, Germany, and Sweden, and Norway. So there's a huge cost associated with the transport and supply chain, which is again the logistic. It can be improved significantly if we can manufacture them in the UK. Operation is one of the most critical one and challenging one, because you have a huge asset in the middle of the sea and ocean, where due to the weather condition, you don't have much access to the asset during the year. So it's like a very small period of time, a window that you can attend. So all the maintenance, all the inspections needs to be done within very, very short periods of time, and monitoring the health of the structures is very important. This is some things that the sector is lacking. There's been huge work, but still not enough. In terms of the commission, in the UK, we are still behind a little bit, simply because in terms of offshore, the first one has been 2000, so the structure are not that old. But the question is because lots of mineral material is being used for the whole structure, from the subsea structure, tower, engine, top power train, and blade, different type of materials. And what do you want to do with the disposal? And there have been a number of different scenarios by different countries, different companies, to see how we can take advantage of this material. So in the last, there are lots of challenges going on. This is obviously a desk-based study, what we've done in NMES, and we try to understand how we can implement it, tests into the sector, and we try to shape a consortium with the key industries in the sector, in collaboration with offshore renewable energy sector, Catapult in Glasgow, and something that we can provide a better service to the basically to the asset owners. And also we want to ensure that how basically we can implement the lesson learned from other sectors like aerospace and nuclear into this. And obviously there are lots of challenges like business models, etc. But this is something that still we are working on that to provide a better service. And thank you so much for your attention.
Saber, quite intriguing presentation. I can start with a question. Regarding the through life services, are there any initiatives on linking the design with the decommission phase in terms of circular economy?
Yes, well, there are. This is it's very difficult to answer yet. Yes, but there have been some work going on, especially in Strathclyde University, and lots of researchers working closely with Vestas and Siemens. Obviously, it worth mentioning we have three leading manufacturing companies in the whole world for offshore wind assets: is Siemens, Vestas, and GE. And all three companies are very active in the UK and working closely with the researchers and academia, and try to understand how they can provide better design, some things more environmental friendly, and some things that they can link it to the end life as well, which obviously reduce the cost for decommissioning. And obviously another factor that's is been going on as well, like other sectors, you have the second-hand parts. So you have a tower, once you dismantle it, you have some parts that you can still use them. There's been some activities going on in the UK that they want to use the same design and the same, basically the used parts, they repair it and they put it back again for the service. They want to keep challenging themselves to reduce the cost. But yes, there are quite a lot of activities going on in terms of design and link it to the decommissioning as well.
Thank you. Quite clear. Dedi, is there any other question from your side or from the
Yeah,
audience?
just follow-up questions from the previous question, because there is a trend in the future. The life cycle will not be a linear process as presentation. Rather, it would be like a relational process. So there will be an interactions between design and surface to the end of life and things like that. So how would you see the framework that you provide can be modified to
Well,
accommodate
basically, what we are working at the moment, this is just desk-based study, and we need to get on with the asset owners to provide us with a more accurate results. And obviously, this is a very tricky question though, because it's very difficult to, because in the offshore wind you have different manufacturers, different geographical location, and different other environmental parameters, basically, which would affect the life in a differently. So since these are new structures, we don't know yet how we can increase that and how we can take the data into account, because at the moment what's going on is, in terms of operation, we collecting lots of data from SCADA, from operation and maintenance, different sensors, etc. But to be honest, still we are working so hard on it to understand how we can take advantage of this data and how we can bring them into work. So I don't think so that there's like a solid answer for that yet, because we haven't got there yet. We don't have a floatable structure, for example, who lasts for 20 years. They've just been implemented this year. This was the first time. Or the big, the oldest one is just Blythe, basically, wind farm, which is only a small 2 megawatt wind farm, which has been very close to shore. And they're not a great example in terms of what's going on for the other assets. So yeah, I don't know how much I can answer your question, but it's very challenging to answer because we don't have that much data yet.
That's great, Saber. Thank you. Are there any questions from the attendees? Nope. So I think we can go to the last presenter.
Thank you so much.
Saber,
Thanks
for your
your
presentation.
Time. Thank you.
Yeah.
So Mariam will be
The next
presenting.
The next work is on a super simple life cycle cost estimation model with minimum data requirements, and the presenter is Mariam. Hi. You're still muted. We cannot hear you.
Sorry, I click on another one. Okay, thank you, Alice and Dedi, for the introduction. I'm Mariam Fassi. I'm a lecturer in True Life Engineering Services and Optimization in Cranfield University, and the work I'm presenting today is on a super simple lifecycle cost estimation model with a minimum data requirement, and it is part of an Innovate UK funded projects that we're running for 4 years, and we are at the mid stage at the moment. This is a collaborative work with 3 leading industries in the UK. So the idea behind this research work comes from one of the challenges within the high value manufacturing sector. And that challenge is when you are having a high value asset, it is the repair, maintenance and overhaul of such assets are coming up with so many complexities and complicated in terms of the data requirements, the accessibility to the data, and the existence of the data first, and also the complexities with regards to the actual maintenance and repair interventions should happen to the asset. And that caused a lot of uncertainties around the cost of maintenance, as well as the whole life cycle cost of such assets. The current practice within the industries are mainly based on looking for the similar projects or similar assets with the same behavior during their life cycle, and a very limited historical data they have to estimate the cost. And for this reason, we come up with the idea of this research that if we can find a simple structure, a simple architecture to estimate the cost, to estimate the life cycle cost, that would help the industry at the very initial stage of the design to realize where the majority of the cost sits, where it comes from, and therefore they can find out how they can minimize it. So there are going to be, so I'm going to just go through quickly some of the concepts. I'm sure you're already familiar with the product lifecycle cost. So this is the sum of the estimated cost in the span of the acquisition until the disposal phase of the products. And for this architecture that we are proposing, we'll look at a kind of a hierarchy of the asset and the equipment. So at the top, we've got the actual equipment itself. But then it goes, which we call it a parent. However, that equipment may come composed of a number of like systems, subsystems, and sub-assemblies, etc. That we call it a child. So this architecture aiming really to estimate the cost at any stage of this hierarchy, whether we are going to estimate the cost of a sub-assembly or we are going to estimate the cost of the major equipment. If you look at the literature review, traditionally, when we are going to talk about the lifecycle costing, one of the top level lifecycle breakdowns comes into the 2 expression of the capital expenditure, CapEx, and the operating expenditure, OpEx. However, there are many other frameworks and methodologies to estimate the cost and to break down the cost levers. Apart from the traditional one, which are mainly rely to the experts' knowledge, we've got the conceptual methods, analytics methods, and heuristic methods. The approach we are going to focus on this study, after the literature review we've done, many of the literatures confirms that one of the, in the presence of enough information and data, the activity-based costing estimations is one of the accurate bottom-up approaches to estimate the cost, and it's simply described as a sum of the cost of the activities, different activities associated to the product lifecycle. So by all this, we come up with a simple architecture for this super simple cost estimation model. So the inputs, the key inputs to this architecture is the cost breakdown structure, is the minimum data requirement that we will that I will explain in this paper, in this presentation, and also the work breakdown structure. Some of the methods and approaches that we take into account was the activity-based costing for the cost estimation, and also the Monte Carlo simulations with the triangle distributions to also look at the uncertainty and also the sensitivity analysis. And the key outcomes from this architecture sits into the outcomes from the sensitivity and uncertainty analysis, and also the life cycle cost breakdown. So where the most cost sits basically during the life cycle. So I simply explained the first input, which is the cost breakdown structure. This is a flowchart that we validate and confirm with our industrial partners in these projects, and this would shows you the key cost event product lifecycle. So the first one is the acquire and install, which mainly focus on the acquisitions cost, and which can include the cost of design concept, the manufacturing, assembly, installation, etc. And then it goes to the operate phase, which at this stage we consider the cost of consumables, and also some of the minor basic maintenance during the operation that should help for the product. During the operation, we have a different cost events, such as loss of opportunity, which we refer to any loss of revenue for the industries due to the lack of availability, due to the lack of credibility, and also performance. Also the cost of disrupt, that is economic consequences of different disruptions to the operations of the asset. That might come into a kind of penalties for the OEMs because they haven't satisfied the warranted and guaranteed agreements with their customers. And also then we have during operations a different cost for the regular monitoring and supports, and also a different investigations going on during the operation. That some of these investigations may comes from the monitor and support reports, or may comes from when the asset goes to some failure or any concerns raised from the customers during the operation. So we are looking at the cost of investigations in that sense. And also after that, if due to some policies or some of the symptoms or the failure happens to the product, it goes to the remove and inspect event, which we are looking at inspecting it, whether we need to disassemble the products, and then the cost of that inspection and disassembly would taken into account at this stage. Then after that, if after the inspections the product have to or the part or component at any level should be rejected, we are looking at the cost of repair or replacement. And if it is going to be any replacement, we are looking at the end of life, the cost of end of life for that sub-assembly or component at this event. And after that, before it get back to the operation, we've got the cost of reinstallation, and then it goes back to the operation. So the second input to that architecture was the work breakdown structure. Again, to keep it simple, we've looked at a very high level work breakdown structures for the different cost events. I won't go through all the details in here, but for example, for the acquire and install event, we just come up with the acquire, assembly, testing, and transport and installation activities. So they would help us to come up with the unit cost of the acquire and install to estimate the life cycle cost. The next input was the minimum data requirement. So the minimum data requirement, we identified what sits with first the time between the overhaul. This can be described as the time between different overhaul events and or overhaul opportunities for the parent products when that child item is going to be inspected. Or at some cases, it can be described as the time between failures. So after that, we have the removal rate. So we are deciding, so after we do the inspection, whether we are going to remove that component or disassemble it or not. So whether it's going to be a removal rate or a 1- removal rate. And after that, we've got a reject rate. So if you look at it as a kind of a probability tree diagrams, the probability of the removal rate will be multiplied by the probability of the rejection rate to give us the rate of reject, and so on after that for the replacement and repair. So again, we multiply that by the probability of the replacement to come up with the replacement, the number of replacement events. So by this means, we can calculate automatically some of the frequency of the events because now we have the rates of them, we know the life cycle of the product, and we can come up with some of the frequencies. So these frequencies comes from those minimum data requirements and can be kind of automatically be calculated. Apart from that, to calculate the life cycle cost, we also need the frequencies to the other events which are not listed in here, and also the unit cost for those events. And after knowing all this, we can estimate the life cycle cost using the activity-based costing approach by multiplying the unit cost of each event by their numbers. And the unit cost of events comes from the sum of the unit cost, sum of the cost of each activity in that events based on the second table that I've presented in here. And number of events comes from, if you've got their frequencies, just simply comes from by multiplying the frequencies to the life cycle of a product. The other things we've looked at is the propagation of the uncertainties in the data. So if you're starting with the minimum data requirement at the top, and we are going to have some uncertainties in the minimum requirement, this is going to propagate to some secondary uncertainties to the other parameters which are linked to the minimum requirement, which going to affect the which are going to end up with the uncertainties in the number of events. And on the other hand, we also have uncertainties in terms of the cost, in terms of the unit cost of each activity, and after that, the unit cost of each event, which then we are going to come up with the propagated uncertainty to the life cycle cost in total.
Mariam, if you can please speed up.
Yes. So to test this model, we come up with a case study from the machine tool. Our minimum requirements are summarized in here, and these are the unit cost and frequencies being calculated for that machine tool that you can see in this table. And then we estimate the cost following the cost breakdown of cost activity approach, and then we estimate the life cycle cost for 30 years life cycle of the asset, which comes to around 4.7 million pounds. So the type of analysis we get from this model. So first, I should mention that this tool at the moment been developed as an Excel tool because we wanted to keep it simple. And all the data analysis and sensitivity and uncertainty analysis been done using the Monte Carlo simulation. And we come up with some information. For example, if we are going to have a plus minus sensitivity variation into the data, how it's going to affect the different cost events. For example, in this example, it's going to impact the replacement cost by 66% in average. and also the sensitivity analysis in a way that how much each cost event would change in terms of in the plus and minus side if you're going to have this uncertainty in the data, and also what is the probability distribution function for our total life cycle cost during these 30 years for that particular case study. So if I'm going to just conclude the outcomes, the first things we've concluded from this study was if you're going to get to estimate the life cycle costing, we should look at 4 main parameters, which are the time between the overhauls or the time between the failures, the removal rate, rejection rate, and replacement rate. And then from the case study, for example, we understand the cost of operation and maintenance is 91% of the life cycle cost, whereas the acquire costs only have 8%, and the disposal cost 1%. And we've realized from the uncertainty propagations diagram that the time between the overhaul has the most impact on the total cost. And also from the sensitivity analysis, we understand that, for example, if we by 5% variation, we have a 21% variation in the total life cycle cost, that 40% of it comes from the reject and replacement strategy events. And also the operation and maintenance really dominate that case study life cycle cost. And the sensitivity in cost data mostly influenced by the replacement cost from that particular case study. And that was it. And thank you for your attention. And please feel free to ask any questions.
Thank you, Mariam. Turns out to be not that a simple cost model. At least in terms of implementation. I can start with a question maybe. When you mention plus or minus uncertainty, do you consider it to be uniform?
No, we use the triangular
even for the input, you mean?
When we've done the Monte Carlo, we've done it triangular. So what we've done is we've come up with the most likely value, and then by plus minus 5%, we variate it to come up with the mean and max boundaries.
Okay, clear enough. Thank you very much. Daddy, any questions, or the audience perhaps? We have time for a few questions.
Yeah, do we have any questions from attendees? Nope.
Okay, I guess.
All right.
Thank you, guys.
So we finished earlier. Thank you, Mariam, for your presentation.
Thank you, Mariam.
It's very interesting.
Actually, thanks to all the speakers, presenters, and the audience. Yeah. I think there's room in the tables in case one wants to continue with the discussions. Yeah.
So I've just got information from Davide that the missing presenter is not attending the conference today. So yeah, we finished earlier. So we can, so after this is a break session, and we will gather again together in the next session in the auditorium at 1. So you can remain in the room, or you can have a chat to follow up some questions that you might have in the session. Yeah, so that's it. Thank you all for your presentation and for your questions and for your attention.
Thank you, everyone. See you soon.